Okay. The sample size required to give you the sample needed, right? And we talked about one sample size already, and it was toward, let's see, it was the bottom of page 3, and it was down here, and we said when sigma is known, this is the sample size we use. And that makes sense because it has sigma, so you have to know sigma. Okay, well, what if you don't know sigma? What if you have proportions? All right, we have another sample size situation. We're going to have z squared times p hat times q hat over e squared. That's going to be our other sample equation. Now, I want to just kind of compare these because students may end up making a mistake with them. So, all right, here is the one where sigma is known, and here is the one with proportions. So let's take a peek. Notice they both have z squared in the top. They both have e squared in the bottom. Then what else is in the numerator depends on the information you have. You have sigma, you square it, you put it in the top, there you go. If you have a proportion and you have p or p hat, remember that's your sample proportion, that's what goes in the top along with q hat. These are not squared. I think it's because they're wearing hats or something, but students tend to want to square them. They want to square everybody. They're not squared, so just take note of that. They're just wearing their little hats. That's just their little thing. Okay, so let's practice this then. So let's say we want to find the sample size needed for, there's your margin of error, 0.03. Here's your p hat, 0.32, and a 99% confidence level. Okay, so let's put our information in. We know p hat, they gave it to us. It's 0.32. All right, now we need q hat though. What's q? How do you find q hat again? Good. 1 minus p hat. Remember, that's one of those formulas that's not on your formula sheet, but we may want to write it on there, and we'll do that when we review. So our q hat is going to be 1 minus 0.32, which is a little 0.68. Right? We have our margin of error, it's 0.03. Now we need a z. So remember, anytime that you are using proportions or sigma is known, we're using this guy, okay? And so Kayla and Maddie, you may want to go ahead and modify this a little bit, kind of the way that I have. These are going to be your z values for your various confidence levels. So this tells us we want a 99% confidence level. Well, 99% confidence level is going to correspond to 2.58 z. Easy enough. That's where we get it from. We get to use that little chart anytime we want, as long as sigma is known or proportion. Okay, now we're going to plug it in and find it. So in our calculator, we're going to have 2.58 squared times 0.32 times 0.68. Remember, those are not squared, over 0.03 squared. Okay. All right, I came up with 1609.37. Okay, good. Now remember, when you're finding sample size in statistics, you always round up. So I'm not going to put 1609, I'm going to put 1610, and that's going to be my answer because you always round up with sample size only. Okay. All right, everybody okay with that? Okay. Now sometimes you'll need a sample size, but we don't know p hat and q hat. We really don't know anything. All we know is the margin of error, which we want to keep small, and we'll know the percent of our confidence level, which will give us a z. But other than that, we don't really know anything about our population. So sometimes they'll ask for a conservative estimate. When they use those two words, that's super secret language for p hat and q hat are 0.5 each. Okay, so they're going to do that to you. They're going to tell you to find your sample size, but they're not going to give you a p hat or q hat. But if you see be conservative or conservative estimate, that's when you just half them, 0.5, 0.5, and that's what you put in. Okay, sound good? All right, last three problems of chapter 8. Okay, let's take a peek at what we have here. So this says given n is 275 and p hat is 0.25. Is the sample size big enough to use the normal distribution to make a confidence interval? Well, we didn't talk about this for this chapter, but the central limit theorem, the good old CLT, is still in effect. Remember this rule. N times p hat and n times q hat have to be bigger than 5. That's the rule. So what they're asking you is, are they bigger than 5? And then you just have to write yes or no. So I'm going to take 275 times p hat, which is 0.25. That's going to give me 68.75. So yes, definitely big enough. Okay, what's my q hat going to be? Good, 0.75. So now I'm going to take 275 times 0.75, and I get even bigger, 206.25. So yes, in both cases, it's big enough. So that's still going to come up, just so you know. Okay, number 2. What is the sample size? We have 2 sample size formulas, one for sigma, one for proportion. Oh, here we go. A conservative estimate. I already know who it's going to be. It's going to be the z squared p hat q hat over e squared. That would limit the margin of error to within 0.27 of the population proportion. This is another way that you know we're looking at this formula for a 95% confidence interval. Okay, well, here we go. I'm going to find my z based on the 95%. So I go to my chart. 95% is going to give me a z of 1.96. And I'm going to square it. Okay, I don't have a p hat or q hat, but I had that little phrase conservative estimate, which means they're both going to be 0.5. Okay. And then my margin of error is 0.27, and I'm going to square that one too. Let's see. I'm not sure what it actually comes out to be, but I think you end up with 14. Just check me and make sure that's right. Normally I put down what I got. Oh, perfect. Okay, so 13.17 is what you come up with, but for an n, you always round up. So that's a perfect example if we go up to 14. Okay. All right. And now let's make a little confidence interval using proportions. Okay, so a sample of 557 observations, that's our n, taken from a population, produced a sample proportion of 0.28. That's p hat. Make a 90% confidence interval for p. Okay, well, since we're using proportions, I'm going to take this 90% and that's going to give me my z. So I go to my chart. We take the bigger number, the 1.65. Okay, there we go. All right, so I have p hat. I'm going to need q hat. 1 minus 0.28. It is 0.72. Okay. All right, let's see if we can remember how to make our confidence interval. So remember, it's not going to be x bar plus or minus the margin of error. Because we're doing proportions, it's going to be p hat plus or minus our margin of error. That's how we get our confidence interval. Then to get our e, because we already have p hat, to get our margin of error, it's going to be z times our well, let me do this. SP hat, but SP hat is that giant square root p hat times q hat over n. Okay, so it's kind of, You got to get all kinds of things to get right up there to it. That's going to be your formulas. All right, so let's start off finding S of p hat. So he's going to be the square root of p hat times q hat all over n. And I got 0.01902. Just go out a whole bunch on that. So you get a bunch of decimal places, or you can just leave it in your calculator. Because now what you're going to do is find E, which is going to be Z times S of p hat. So you don't even have to round S of p hat if you don't want to. Once you find it, you can just multiply it by 1.65. I came up with 0.03119. Then once you find your margin of error, you're just going to subtract it from p hat and add it to p hat. Okay, so now I'm going to have x bar plus and minus e. So I'm going to have, not x bar, good gracious, hold on, p hat. Okay, so I'm going to have 0.28 minus 0.03119, and I'm going to have p hat plus 0.03119. Okay, and that's going to give me a nice little interval of 0.249 to 0.311. And there we go. And remember, if this had asked you for a percent interval, you would just make this 25% to 31%, right? You would just move your decimal point over once you find this if they had wanted a percent. Okay. Now there's one more question to this problem, but I just want to make sure you're okay with your interval. Everybody get their interval all right? Okay, the second part of this question says the true proportion, not the sample proportion, is 0.25. Does the confidence interval cover this? All it's asking you is, this was just an estimate. Does the real answer, the true proportion, fall between these two numbers? Yeah, it does. So we would put yes. Now, if it didn't, you just put no. That's perfectly fine. It's an estimate. Sometimes it works, sometimes it doesn't. So it's not like any shame on your family. It's just you put no and you're good. Okay. All right, so that's chapter 8. You have all your little intervals and you have your 3 scenarios: sigma known, sigma unknown, and your proportions. Okay, sound good? So we're going to kind of put this aside, compartmentalize him in another portion of your brain for a little bit. We'll come back to him next week and review. Okay, just let him marinate in there a little bit. And now we're going to talk about, would you believe I didn't get a packet after all the time I told y'all to go get a packet? All right, so I know it's a lot because normally we do 5 million of these things to the point of doing them in your sleep, but that's okay. All right, the other thing you have besides the novel is I made you a little cheat sheet. This is what I always give out to students to use on the test, because hypothesis testing is too confusing to just turn you loose with your memory. And the key formula sheet has gotten you so dependent on having formulas that you kind of forget how to memorize. And this stuff's not on the key formula sheet. And so it kind of leaves you in a lurch for test 4. So I always let everybody use this little guy on test 4. So this first page here is just kind of an overview of everything we're going to learn on the first page here. And then if you notice, you've got 3 little scenarios inside. They're the same scenarios from chapter 8. Sigma known, sigma unknown, proportion. Okay, but now with hypothesis testing for each of those 3 scenarios, there's 2 ways to approach a hypothesis test. There's the critical value approach, and there's the p-value approach. So 2 different ways for each scenario. So that leaves us with like 6 possibilities, which is why I always kind of like to give you the little cheat sheet to use. Okay, so we'll get to this in a minute, but let's just start from the beginning then. Okay. So what in the world are hypothesis tests? Well, if you have ever done a science fair project, especially if you've ever been in Miss Reister's class, she's really big on science fair projects, on hypothesis testing, alpha testing, all that kind of stuff. So you may already know how to do some of this. But hypothesis in statistics is a little different than a hypothesis in science. You're still testing a theory, but we just take a more black and white approach. So, okay, let's talk about it here. There are two types of hypotheses. That's the plural version. So we have the null and we have the alternative. Okay, your null is HO. Your alternative is H1. H1 is the one that you're testing. That's the one that you're going to do the test on and then look at the values and declare true or false. Okay. All right. So the null, though, is a claim or a statement about a population parameter. That means either mu or p, because X bar and P hat are sample statistics, right? Now, the important part here is the null is always assumed to be true unless you can prove it's false. All right, we assume it's true. So it's kind of like, I always kind of compare hypothesis testing to like the justice system. It's kind of like you are assumed innocent until you are proven to be guilty, right? Even on trial, you're assumed to be innocent unless they can prove that you're guilty. We assume the null is true, no matter what. We assume it's true until we can prove that it's not. Does that make sense? Okay, the alternative is another claim about the same population parameter that will become true if the null is false. So it's like, if the null is false, this is your new reality, is the alternative. It's the new thing that's going to be true, okay? So here's the other funny thing. You can't reject or accept a null. You can only reject or fail to reject. We never say we are going to accept the null. We either say we're going to reject the null or we're going to fail to reject the null. I know it's really strange. There's a lot of weird wording in chapter 9, but that's the lingo, okay? And after you have completed a problem, you will have to use that lingo. You will have to tell me, reject the null or fail to reject the null. You will have to put that statement one way or the other down there, okay? All right, so we're going to reject the null if it's false, which means your alternative is true, okay? Then what we're going to do is we're going to draw, if we use the critical value approach, we're going to have our little curves, and then somewhere in the curve, and we're going to talk about it in a minute, you're going to have some type of region that's shaded in that we're going to call the rejection region. So we're going to be finding some numbers, some values. If your values fall into the rejection region, you reject the null. If your values are in the non-rejection region, then you fail to reject the null. So you're going to have a region that would be the rejection. I always shade it in, call that my rejection region. You're also going to have critical points. Sometimes these are called critical values. They're the little value on the number line. Sometimes there's one, sometimes there's two, that separate the two regions from the rejection and the non-rejection. The point right there that separates it is your critical point, okay? Now you're also going to have two types of errors that can occur. Your type 1 error, also called an alpha error, that's supposed to be an alpha. Normally my alphas look like fish, but the computers looks like little italic A's for some reason. These are errors that can occur when a true null is rejected. This is the worst error you can make. Like you get kicked out of math, right? Like the worst error. This, when the null is true, but you rejected it. It's kind of like when an innocent man, right? True, goes to jail. That's really the biggest travesty in the justice system, is when somebody who's innocent goes to jail. So this is like the worst kind of error. True null gets rejected. All right. The significance level, or alpha, is just the probability of making this error. That's all. And we're not going to worry about any of these crazy things in here because we don't use them. Now, type 2 error is called the beta error. Now, in the beta error, this one's still bad, but it's not like you're fired and have to leave, right, in shame. This one occurs when a false null is not rejected. So the statement's false, but you didn't catch it, right? So this is kind of like a guilty person goes free. I mean, it's not great, but at least you didn't put an innocent person behind bars, right? So it's false, but you didn't catch it. Whereas this one was true and you got rid of it. So those are the two. This one's the worst kind. Okay. And then beta is simply the probability of making a type 2 error. Remember, alpha is the probability of making the type 1 error. And then we don't need to worry about the power of the test. We don't teach that anymore. That's left over from an old book. So I apologize. Okay, so let's talk about possibilities for the test. Okay, so I already told you the 3 scenarios still hold true: sigma known, sigma unknown, proportion. But we can also have different types of tests. So we can have a two-tailed test, which means that your rejection region is in both tails. It's two-tailed. That makes sense. You have a rejection region in both tails. So let's kind of draw a picture of what that would look like. Okay. You would have, and they're usually really symmetric. Mine didn't come out that way when I did it, but here you go. Okay, you've got 2 rejection regions. This in the middle, I'm going to call the non-rejection region. Okay. And then because you have 2 boundaries, you're going to have 2 critical values or critical points. Critical 1, critical 2. They're going to be the same numeric value, but one's going to be negative and one's going to be positive. Okay. All right. And then our alpha is really, if you're using the critical value region, your alpha is the area in rejection region. This is another definition for alpha, which we already said was also the significance level. Okay. So if I have 2 rejection regions, I'm going to have to split my alpha in 2. So this is going to be alpha over 2, and this is alpha over 2. That's what a two-tailed test is going to look like. Now, I know this looks absolutely crazy. Chapter 9 is really foreign when we start it, but then it gets so easy. It's really easy once we get going. Okay. All right. Now, anytime you do a hypothesis test, you're going to have to write a null hypothesis and you're going to have to write an alternative hypothesis. So we'll get into all that later, but anytime you have a null, you're always going to use an equal sign. So all of these nulls are going to get equal signs. So that kind of makes it hard to tell what kind of test you have by looking at the null. You're going to always look at H1 to determine the type of test. We're not going to look at HO because HO doesn't really tell you anything. They all look the same. So for a two-tailed test, the way that you know that it's two-tailed is your H1 is going to be not equal to. When you see this, you know it's a two-tailed test. Okay. Another way, in case you have to write it from the beginning, is that you might see the word different. They want you to test to see if the true answer is different. Not more than, not less than, but different. That's going to be a two-tailed test. All right, let's look at left-tailed tests. Well, you can probably guess exactly what this one's going to be. Your rejection region is in the left tail. Okay, so here's my curve. He got a little smushed down. I only have one rejection region, so the whole thing is alpha. I don't have to split up alpha. This whole side is my non-rejection region. And I only have one critical value. All right, my critical value is going to be negative because it's on the left. Any critical value on the left is negative. Any critical value on the right is positive. That makes sense according to what we've done before from way back in chapter 6, I think. All right, so our null is going to be equal, okay? Our H1, the way that we tell it's a left tail is because it's going to say less than, right? So if it says less than in your sentence or smaller than, or if you see a less than sign, that's your indication we have a left tail test. We need to set it up like this, okay? All right, right tail is going to be just the opposite. We're going to have a rejection region in the right tail. There we go. We only have one shaded region, so it's alpha. Here's our non-rejection region, and we have one critical value. And since he's on the right, he's going to be positive. Okay, and his H1 is going to be greater than. So if you hear greater than, or bigger than, or more than, you have a right tail test. And that's what you're dealing with. And then of course, this last little part here deals with the CLT, hasn't gone away, which means N times P needs to be bigger than 5, and N times Q needs to be bigger than 5. That's not going to change. So what you did here on this page is pretty much what you see on the front of the little cheat sheet that I made you, right? It kind of gives you everything you need, okay? So is it okay if I move this? Okay. All right, so let's look at this back here. What you're gonna find is on your Wiley quiz, this is gonna help you on the quiz. So let's just talk about this real quick, and then we're gonna jump into examples. And we're gonna do a couple of examples of sigma known, couple sigma unknown, couple proportion, okay? All right, so this is kind of a funky little chart. It's the only chart I could find, but I think it helps a little bit. So let's see. So these are Wiley quiz questions. All right, so let's say that the null was true and you did not reject it. Well, that was the right decision, right? So the null was true and you decided not to reject it. Well, good job. That was, oh, I should have put correct decision. Sorry, my bad. Correct decision. Okay, nice job. Okay, now let's say the null was true, but you rejected it. What kind of error is that? That's a type 1 or an alpha error. So Wiley's going to give you scenarios like that. They're going to say your null was true, but you chose to reject it. And then you have like multiple choice of whether that was correct or what kind of error it was. And you're going to write type 1 error or alpha error. Okay. All right. What if your null is false, but you don't reject it? That's your type 2 error or your beta error. Okay. What if your null is false and you do reject it? Well, that would be correct. So these are kind of your 4 scenarios that you could, come up with in this case. Okay, this next little chart, probably not even important that we do it because we've already kind of done it, but let's just say, okay, in this case, you have a shaded region or rejection regions in both tails. So what kind of tail is this test? Two-tail. Okay, so what kind of sign are you going to give the null? Equal. You always give the null an equal, right? So what kind of sign are you going to give the alternative for a two-tailed test? Not equal, right? for a two-tailed test, your H1 is not equal. Okay, now I have a rejection region in the right tail. Well, I just gave it away, didn't it? So that's a right tail test. Okay, now the null is usually an equal sign. What does the alternative have to be for a right tail test? Greater than. Now, sometimes you'll see the null not be an equal sign. You'll see it as the opposite sign of your alternative. So you might see it as a less than. That's why I kind of wrote it on my little cheat sheet for you, that sometimes you'll see the null as the opposite of your alternative. Okay, and now my shaded area is over there. So this is a left tail test, okay? And the null could either be equal or greater than, as long as your alternative is less than, okay? And then it kind of wanted to know what these little stars represented down here. Those are your critical points or your critical values, whichever one you want to refer to it as. And then let's get ready to jump right in to some examples. Okay, we ready? So we're going to do number one, okay? Whenever we're going through and we're doing examples, you have to decide three things for every example. First thing you have to decide is, which page are you going to be on? Is it sigma known? Is it sigma unknown? Is it proportion? Okay, once you figure out that, you have to decide, okay, is it a p-value approach or a critical value approach? Because there's two ways to do hypothesis. And people don't do both. Students, people, statisticians, they always find one way they like the best and they stick with it. But in here, I have to teach you both and you're tested on both. So you don't get to decide what you like till later. So according to the problem, you got to figure out which one they want you to do. Then the third thing you're going to have to decide is, what kind of test is it? Left, right, two-tailed, right? So those are your three things you got to decide. So here we go. We have a random sample of 120 observations. It produced a sample mean of 29. Okay, so N is 120. Sample mean is X bar. Chapter 9 is when you really, the rubber hits the road. You got to know what these symbols are, right? You have to know what is X bar, what is sigma, what is Z. You have to be able to figure this stuff out. Okay. Find the critical, okay, so I'm critical value approach. That told me that, okay. And observed values of Z for the following test of hypothesis using alpha equals 0.01. All right, I have my alpha. The population standard deviation is known. What's the population standard deviation symbol again? That's your sigma. Okay, that tells you what page to be on. So automatically I know I'm on the next page, sigma is known. And I want the critical value approach. So the approach down here at the bottom. And then you just got 3 steps and you're good to go. Okay, everybody see that? We figured that out? Okay, now I still need to know what kind of test I have. Turns out they gave us the null and the alternative. They're baby stepping us in. Okay, I can't tell anything by the null, but let's look at H1. So what kind of test does this tell me I have? Two-tailed. This is a two-tailed test. Okay, so now we're ready to go. All right. First thing I always like to do is draw my picture. Now, I'll be honest with you. I don't draw a picture for the p-value approach because in the p-value approach, everything means something different. It's kind of like Bizarro World. So I don't even draw it because it's too complicated. But I do draw it when it comes to critical value. So here's my two-tailed critical value approach. This is my non-rejection region. Okay. Going to have a negative critical value here and a positive critical value here. Okay. I'm also going to go ahead and draw my alpha in here, my area under the curve that's rejected. So alpha divided by 2, that's going to be 0.01 divided by 2. Do that in your calculator because decimals are funny things. It's not 0.05, it's 0.005 for each region then on each side. Okay, now we're going to just follow our directions. So I'm down here. First thing it tells me to do is calculate Z observed from the formula. Turns out my formulas are right here. Okay, I want you to write that Z observed is also called the test statistic. Just to give you one more thing to confuse you, is that I think Wiley calls it Z observed, but our department head calls it a test statistic because she's, you know, quite up there in her years, and that's what they called it way back in the Stone Ages. So she still refers to it as that, even though we don't call it that in our book and we don't call it that in our curriculum. That's what you're going to get on test 4. And I don't want you to get confused when we get test 4 and they ask you for the test statistic. They're talking about Z observed. She just refuses to call it that. Okay, so here we go. First thing we want to do is calculate Z observed from the above formula. Okay, so Z observed, which is also our test statistic, is going to be X bar minus mu over sigma X bar. And then if you look next door to the formula, it tells you sigma X bar is sigma over square root of n. Okay, so here we go. Let's find it. All right, X bar, that's our sample mean. We got it from our paragraph up there. Okay, minus mu. Everyone always has a really hard time finding mu. Mu is your null. And I even wrote that right here on your little cheat sheet because people can't ever find it. So it's right there on there. You get that from your null. So mu is 28 over sigma X bar. Now we have to come up with that. He's actually sigma divided by the square root of n. Okay. So depending on, I just put that whole thing in my calculator like that and it comes out just fine, but that's up to you. You should get, I believe, 1.22. Got that? Good. Okay. Make sure you can get that. That's a lot of, you can baby step it in and use different steps if you want, or you can stick the whole thing in parentheses. Sound good? Okay. All right. That was our first step. Okay, now this says find Z critical using alpha as the area in inverse norm. Okay, if it's a two-tailed test, divide alpha by 2 first. We have a two-tailed test, but we already divided alpha by 2, remember, right here, and got 0.005. So we're going to use our calculator and we're going to go to inverse norm. So remember, that's under distribution. Get out of the glare. Here's inverse norm. I already have 0 and 1. All I need is alpha, but it was a two-tailed, so I had to divide it by 2 first. I already handled that. And I get negative 2.58. Negative 2.58. Everybody get that okay? When they put it in inverse norm? Not normal CDF. Make sure it's inverse norm. Okay, what they just gave you there is your Z critical, your critical value. Now they gave you a negative value. Which critical value do you think it is? The one on the left or the one on the right? The left, because it's negative. I already forgot what I said it was. Negative 2.58. Okay, so how do you think you get the one that's on the right? You use the same one, you just make it positive. So my Z critical right is positive 2.58. My Z critical left is negative 2.58. I've got everything I need. Okay, that's all this problem wants, but we're going to go ahead and finish it. Look what number 3 says. Draw the standard normal curve and label it. We already did. Check to see if Z observed is in a rejection region. So here we go. We put our critical values in. Where does 1.22 fall? In the non-rejection region. Does everybody see that? Because remember, this is negative infinity, this is positive infinity. So this is in a non-rejection region. So we are going to fail to reject the null. Non-rejection means fail to reject. That would be our final statement. Okay. So on test 4, it's still multiple choice. This is what they're going to ask you. They're going to have 3 questions per test. First question is going to be, what are the critical values? Second question, what's your test statistic? That's your Z observed. Third question, do you reject or fail to reject the null? Okay, so 3 parts to every test. Does that sound okay? There's actually 3 parts. There's actually A, B, and C. It's like, do you fail to reject? Do you reject? Or do you not have enough information? Don't ever pick that. I don't know why they put that. You always have enough information. Okay, it's got to be one of the other 2. But that's how you run a hypothesis test. Is that okay? Got it? Okay, let's go look at number 2. Okay, this is going to do the same thing, but a different type. We're not going to do number 3. Okay. All right, let's see what we have in number 2. So remember, we need to know sigma known, unknown, or proportion, p-value or critical value, and then what tail. Okay, so we have a random sample of 16 observations taken from a population, produced a sample mean of 75.4. All right, and a 16, X bar is 75.4. Okay. Population is normally distributed with a standard deviation of 6. What is 6? It's our sigma, right? That's our population standard deviation. Now we know we're going to stay on this page a little bit longer. Sigma's known. We're going to stay here. Okay. Then I noticed they already give me the null and the alternative. I notice this is a greater than. So what kind of tail am I looking at now? Greater than is going to be right tail. Okay, so that's what I'm looking at. Then I go on and I read A and it says calculate the p-value. Okay, so I'm going to be up here this time on the p-value approach. Now I don't draw pictures for the p-value approach because it's too confusing for me, honestly. Because alpha is no longer the area under the curve. There's no critical values. It's really different. So I just kind of follow my little directions and that's what gets me through it. So here we go. Directions say, calculate Z observed from the above formula. So that's the good news. No matter what approach you use, you have to find Z observed. You will always have a test statistic. Okay. So here we go. I know I'm not to my p-value yet, but I'm just going to follow the directions. So I'm going to do my Z observed. I'm going to have X bar minus mu. What's my mu this time? 72, right? Don't forget he comes from the null. Don't forget that. Okay. Divided by sigma x. But remember, he's going to be sigma divided by the square root of n. Okay, so my Z observed, let's see, what did I get? 2.27, no good, okay. All right, we did it. Okay, let's go to our next step. Okay, next step says, right all over everything. Okay, using Z observed, that's why you had to get it first, find the area under the curve using normal CDF. So now you're in your calculator, normal CDF. All right, here's the deal. If it's a right-tailed test, here's what we're putting in. A left-tailed test, here's what we're putting in. If it's a two-tailed test, you can use either one, but you got to multiply your answer by 2 because you got 2 tails. We're finding the area under the curve. For a critical value approach, you consider your alpha your area under the curve. For a p-value, you don't. You're actually finding it, so it's different. They're just coming at it from 2 completely different places, okay? This area under the curve that you find, this answer, to your normal CDF is your p-value. So once we find that, we're going to have our p-value. So here we go. We're going to do normal CDF. Okay. We have a right-tailed test. So Z observed is our lower bound. Positive infinities are upper bound. 0, 1. Okay. And this is going to give me my p-value. All right. So if I put that in my calculator, I came up with 0.0116 as my p-value. Okay, you can kind of see that you can't do chapter 9 until you've done chapter 6 and 7 and 8. Like it just totally builds, right? You have to have all these different skills. All right, so that's the answer to A. That was my p-value. Okay, now B and C want you to compare the p-value to a significance level. Now remember, your significance level is actually alpha. They're going to give you 2 different alphas and want you to compare them to your p-value. That is super strange. That is not at all how we figured out critical value, right? That's why you get a cheat sheet, because it's like your brain's going to explode. Here's the deal. Look at number 2. Compare your p-value to alpha. If your alpha, if your significance level is bigger than p, reject the null. If it's less than p, fail to reject the null. As far as statistics goes, the smaller the p-value, the more significant it is. The smaller the p-value, the more you reject, okay? So this is kind of in a nutshell how you're going to know whether to fail or reject. So let's see. This tells me for B, my significance level is 0.01. That's my alpha, okay? My p-value is 0.0116. What do we think? Is alpha smaller or bigger? Hopefully you realize it's smaller, right? If you want to, you can add on some more zeros so they have the same number of digits to kind of help you compare it, but it's smaller. So if alpha is smaller, we're going to fail to reject the null. And that's what you would write. Fail to reject null. Okay. Now we're going to look at C. C says, oh, it's supposed to say what if, sorry. What if the significance level changes to 0.025? What about in that case? Is alpha now bigger or smaller? Definitely bigger. And if alpha is bigger, then we reject the null. So that's how you do a p-value approach. They're completely different. I mean, they are absolutely opposites. Does everybody see that? Critical value uses inverse norm. P-value uses normal CDF. Critical value uses alpha as your area under the curve. P-value is the area under the curve, and you compare it to your alpha. So it's like, holy cow. So I really hate that they make you learn both, because it's like learning, you know, about like cats and zebras, you know, it's like, So this though will kind of help you just be familiar with it and kind of go through it a little bit. So, okay, let's skip it on over here to, I was gonna do, I'll tell you what I was gonna do, 4, 6, 9, 12, and 14. 4, 6, 9, 12, and 14. So let's try 4, see if we can get 4 in. Maybe we'll get 6 in, okay. Then we'll see how we go. Okay, those were the numbers I was gonna try to get in. 4, 6, 9, 12, and 14. Okay, we'll see. Anyway, we still have review days next week. We'll get it. So, okay, manufacturer of auto batteries. Anytime you have like a consumer agency that's testing warranties, they do hypothesis tests. That's what they do. Okay, so manufacturer of auto batteries claims that the mean life of the batteries is 45 months. All right, we have to set everything up here. This is a true hypothesis test. Like this is not a drill. We have to say it all. So what we're going to do is have to compare and come up with a null and an alternative ourselves. This first sentence, 99.9% of the time, is your null. Okay, so this tells you the manufacturer of auto batteries claims the mean life of the batteries, didn't say sample, it said mean life of the batteries is 45 months. That's your mu, that's your null, and it normally is. Okay. A consumer protection agency wants to check this claim. They took a random sample of 24 batteries. Okay, N is 24. They found that the mean life for this sample is 43.40. Okay, so what is 43.40 going to be? It's the mean of the sample. Here's your X bar. Good. Okay. Using a normal distribution with a population standard deviation, what does that mean? Sigma of 4.5 months. This was going to be the last sigma I did. I just wanted you to set up one from the get-go. So we're doing sigma. Find the null, the alternative, and the p-value. Okay. When the alternate hypothesis states that, so here's our H1, here's our test, the mean life of these batteries is less than 45 months. So what kind of little symbol is he going to get for a less than? Well, it's a less than symbol, most of them. But what kind of test is that going to be? Left-tailed. Less than left-tailed, greater than right-tailed. Okay, does that make sense? Okay, so we know we're doing sigma known one more time. We're going to use the p-value approach because that's what they asked us to find. And we're doing a left-tailed test. So I'm not going to draw a picture because it's too complicated, but let's jump right in and see if we can do this real quick. Okay, so we already found HO, we already found H1, we still need the p-value. Then they tell us, will you reject the null hypothesis at a significance level of 2.5%? That's normally how they give it to you. Significance level is alpha. I don't want it at 2.5%. I want a decimal. So divide by 100 and you got your alpha to compare in the end. So you have all your information, okay? So here we go. Sigma known, p-value. First step, calculate Z observed right here, okay? So here we go. Z observed, also called the test statistic, is going to be X bar minus mu, remember he's from the null, divided by sigma divided by the square root of n. Okay. And don't be scared if your Z observed ever comes up to be negative. In this case, it will, and that's okay. It doesn't mean it's wrong. It just means, you know, your Z values can be positive or negative. He's just over there. With a left-tailed test, you're going to expect almost everything to be negative because you're in that little negative left region, right? Okay, now we found that. Okay, second step. Using this, find your area under the curve. We're going to do normal CDF. Now remember, this is a left-tailed test. So think about a left-tailed test. Negative infinity is your lower bound. What's your upper bound going to be? Z observed. And I even wrote it on here for you in case you forget that. And 0, 1, right? Okay, so we're going to do normal CDF. We're going to do negative infinity. We're going to do Z observed, 0 and 1. Okay, this is going to be the p-value, whatever this comes out to be. I came up with 0.0409 as my p-value. So that was the other item that they wanted. Okay. Then the very last sentence said, will you reject it? Right? So we have an alpha of 0.025. We have a p-value of 0.0409. What do we think? Alpha smaller or bigger? Smaller. And according to this, right, if alpha is smaller, you fail to reject the null. Okay. And there you go. Is that one okay? All right, let's try. I think I can squeeze in an unknown real quick. Okay, because it's, well, 6 is super easy. Sorry. Of course I can squeeze that one in. I don't know that I'll get to 9 today, but okay. Everybody okay on that one? All right, I'll just kind of stick this over here for a second then. Let's go look at number 6. We're going to skip over to there. This is a Wiley quiz question on number 6. Okay. All right, so number 6 says, for the following significance level, what is the probability of making a type 1 error? All right, you got to go back to the front of either the cheat sheet or the front of the packet. But if alpha is 0.06, that is the probability of making a type 1 error. They're the same thing. If you go back here, look, alpha is the significance level. It's also the probability of making a type 1 error. They're the same thing. This is just the front of your little cheat sheet. So your answer is going to be 0.06. It's a trick question, basically, is what it boils down to. They're the same thing. Okay. All right, let me just talk about number 9, because number 9 is where we're going to pick up next week. Okay. So number 9 and number 11 are both sigma unknown. So we're going to do those. And then number 14 and number 18 are proportions. So then we'll do those. Okay, but let's just walk through and set up number 9, and then we'll do it the next time. So this is super tricky, and that's why I want you to just read it real quick. So a random sample of 18 observations from a normally distributed population produced a sample mean of 42.6. You guys are super good at knowing that's X bar. Then look what they do. And a standard deviation of 8. Well, hold up, Ms. Holcomb, that's standard deviation. That's a sigma known. It's not, because look where they put it. It's in the same sentence as all the sample information. It is super sneaky, but that's S. This is sigma unknown. So if they tell you very specifically it's a population standard deviation, then it's sigma. If they start out talking about a sample, there's 18, made a sample mean of 42.4 and a standard deviation of 8, that's them tricking you. That is a sample standard deviation. Does everybody see that? That's like classic FSA reading comprehension right there, right? Like it's, and I'll be honest with you, it still gets me sometimes. I'll be scanning the problem and I'll just write that as sigma. So this is sigma unknown, okay? And so, and then of course our significant level is 0.01, all right? This is a real stinky one. Wiley does this a lot. It wants the p-value approach and the critical value approach. So we're actually going to do this problem twice. We're going to do the p-value and the critical value. And then what kind of tail am I going to have for this guy? 2-tailed. Okay, well, we'll stop there. I just wanted you to see that that sigma unknown is not quite as straightforward as you might think it is. But we will get this finished on Tuesday. I'm not worried. You're still going to get everything you need to know.